Hi, and welcome to this video about Tsirelson space, which is a construction in Banach space theory. It's the first example of a so-called non-classical Banach space. And so it was quite an ingenious construction back in the 70s, and we're going to build up all the theory necessary to describe it. So there's going to be a lot of definitions in this video. I'm going to try to keep it under 1 hour. And I do want to keep 2 proofs in there. So that means that we're going to have to take a lot of lemmas and sort of other theorems for granted. I'll state them, but I won't give their proofs in the video. That being said, I do have notes that are in the description that I've typed up, and there's like 19 pages of them with all the proofs and everything. So if you want, you could, when I state a theorem and say the proof is in the notes, you can pause and read the proof, or try to think about it yourself. Those are for the skeptics. For the non-skeptics, you can just take it on faith. That's kind of what I do. Anyway, so we're going to start with what a norm vector space is. So a norm on a vector space is a function. It's denoted with the double bars from the vector space V to R with, okay, my writing is pretty messy, so that's another reason why you might want to read the notes. There's 3 properties. So the first one is V is non-negative for all V in V. The second is that if you scale a vector V, you want its length to be the modulus of the scalar times the length of the vector. So this is for all scalars alpha and V in V. So the scalars come from the real or complex field for our purposes. And thirdly, we want the triangle inequality. So the triangle inequality says that the length of V plus W it's an inequality. It's less than or equal to the length of V plus the length of W. Okay, so this defines a metric space with, so the distance, so metric space. Because we can set the distance from V to W to be the length of the vector V minus W. Okay, so any norm vector space is a metric space, and if it's complete, so a complete norm vector space is a Banach space. Okay. So we're going to be playing with Banach spaces in this video. Okay, so what are some examples of Banach spaces? Well, you might have heard of them. So examples. You could take, so there's what we call LPN. So this is the space of n tuples. So x is equal to x1 up through xn with this sum, so I equals 1 to n of the xi's power p, and then you take the pth root, and we want this to be finite. And if this is finite, then we can set this to be the norm of x, and you can check that it satisfies 1, 2, 3. And of course, this is one example of this is just n-dimensional Euclidean space. If you take p equals 2, you square the inside, and then you take the square root, and that's the length of a vector by, I guess, Pythagorean theorem. And so we're very well acquainted with this Banach space. Okay, if we remove the n, so we can define LP, and this is the space of x. And now we're going to have infinite vectors. So they're just xi for I equals 1 to infinity. And it's similar. We just want this sum, but now we go up to infinity. We want this sum to be finite. And if the sum is finite, we can set this to be the norm. And we get an infinite dimensional Banach space. Okay, so we're going to be playing with LP. And oh, I guess here I've been just writing p. What is p? P is just a number from 1 greater than 1, but less than infinity. So here's When we have p going to infinity, or p equals infinity, I guess, the limit of these p norms that we wrote there is the supremum. So what is that? So L infinity is the space of sequences x, which is xi equals 1 infinity with, okay, and we want, it's not a sum anymore. It's the norm of x is going to be the supremum of n greater than 1 of x pi. We want this finite, of course. That's L infinity. So these are sequences, and you take the maximum of all the coordinates, and that's the norm. Okay, so this also defines a norm vector space. It's complete. And another, if we take C0 subset of L infinity, C0 is the space of convergent sequences. I guess not even convergent. These are sequences that converge to 0, and it's a norm vector space as well. It's a subspace of L infinity. We take the norm to be the supremum, because if it's a convergent sum, then it has to be bounded, and so it has a supremum, a finite supremum, sorry. And so it's a subspace of L infinity. It's closed, which means because L infinity is complete, it's C0 is also complete, so it's a Banach space. Okay. If we let the support of x be the set of all I in n, the indices such that xi is non-zero, so that's the support of a vector. C00 is the space of sequences with finite support. So these are infinite sequences, but all but finally many terms are 0. So past a certain point, we get all zeros. This space is not a Banach space. And how do we see that? Well, if we take the sequence 1, so let's say xi is equal to 1, a half, a third, all the way up to 1 over I, and then we continue with zeros, sorry. So each of these xi's are in C00 because they're finitely supported. And the difference between two xi's, well, they're the same for a while, and then they differ at one place, and the size of that coordinate is 1 over I. So so that their differences go to 0, which means the sequence is Cauchy. Now it's a Cauchy sequence, but then its limit is this infinite sequence of all the 1 over n's, and that is that's not in the space, right? That doesn't have finite space. So this is C00 is a norm vector space, but it's not a Banach space. Okay, but what you can do whenever you have a norm vector space is you can just define a Banach space by taking the completion of the space with respect to some norm. And so that's what we're going to see later. We're going to actually use C00 to define a Banach space with respect to some norm that we put on it. Okay, so let's continue. It's going to be sort of definition central here. So we're going to need a couple definitions about the dual space. So let f from x to r be linear functional. So it's linear functional. X is a norm vector space. X is a norm vector space, and this is a linear function. It's continuous if and only if it's bounded. Okay, and that's something that's just a fact. And so the x infinity is the, sorry, not x infinity, x star is the set of all bounded linear functionals on x. Okay, so we're going to define a type of convergence in x. So if xn is such that there is x, and so we want x in x. So if xn is such that there's an x from such that, I just said such that twice, f of xn converges to f of x for all f in the dual space, then we say that xn converges weakly to x. Okay, so I mean, if xn actually converges to x, then this has to hold for every functional. You know, if we're getting closer and closer, then because they're around linear functionals, we're going to get closer to x also. But there's a weaker notion of convergence, and that's this converging weakly. It's just, you know, you may not actually converge, but for every functional, the functionals don't know that, basically. As far as the functionals are concerned, xn converges to x. So it converges to x if x equals 0. We say that it is the sequence of xn is weakly null. Sorry, it's hard to write at the bottom of the screen there. It's weakly null. Okay, so that just means it converges weakly to 0. All right, so that's it for dual spaces. We're not going to use much more from that. Now we're going to talk about bases. Okay, so in a finite dimensional linear algebra, we often use basis, and we want bases in infinite dimensional vector spaces as well. But if we want to do analysis on them, then we want them to sort of behave well with respect to the norm. Okay, so we need to define a Schauder basis. So a Schauder basis is a sequence EI, I guess in X. So it's Schauder basis of X. The sequence EI is such that for all X in X, there is a unique expression of X as a convergent sum, I equals 1 to infinity, of AI EI. And here the AI are scalars, and the AI depend on X, obviously. And by unique, I mean that if you give me different AI, we get a different X. Okay, so X has a sequence of AIs and only one sequence of AIs. Okay, and so the convergence, I mean, this has to be convergent sum for this to make sense. And the convergence is with respect to the norm of X. Okay, and this is in a Banach space of X. So a sequence EI for which there is m greater than 1 such that 1 over m is less than equal to EI, less than equal to m for all I. So if you can kind of sandwich EI, all of them between the same two 1 over m's and m's, then EI is semi-normalized. Okay, and if m is equal to 1, then it's normalized. Okay, so in linear algebra, I'm sure that you've talked a lot about orthonormal bases, and so the normal means length 1, and so we want length 1 vectors as well, and that's a normalized basis. So that means you set m on both sides to 1, and so all the EIs have length 1. Okay, so sometimes we'll have normalized bases for the rest of the video. Sometimes we'll only have semi-normalized ones, but we find that both of these types of bases are pretty well behaved. And actually, it doesn't even need to be a basis. It could just be a sequence. And why that's kind of important is because sometimes we're not going to have a basis, but any sequence xi that is a basis for span of xi for the closure of its linear span is called a basic sequence. Basic sequence, okay? So we might take a sequence, and any sequence spans some subspace of the Banach space, and that might not be a Banach space itself, but if we take the closure, then it's now closed and thus complete, so it is a Banach space. So that span xi bar is a Banach space, and any sequence that is a basis for its for this Banach space is a basic sequence. Okay, so they're almost, you can think of basic sequences as bases. just not of the whole space possibly. Okay, so now we're going to talk about what it means for two bases to be equivalent. So two bases, xi of x and yi of y are equivalent if the map xi to yi extends to a linear homeomorphism x to y. Okay, so linear homeomorphism is kind of our notion of isomorphism with norm vector spaces. And so it basically means that x and y are isomorphic in some way, and they're isomorphic topologically, which doesn't mean that the balls are sent to balls of the same size. So an equivalent definition, so equivalently, there exists a small m and a big M such that small m times the sum of ai yi is less than or equal to the same ai's. You take the sum though of ai xi, and that's less than or equal to big M of sum ai yi. Again, these are all infinite sums. And remember that, I mean, if these are bases, so every x has a unique expression as sum of ai xi. So what we're saying is you take an x and x, and now we extract its coefficients with respect to the basis xi. And now we use the same coefficients in yi, which is supposed to be some kind of equivalent space. So you get its sort of analog in y. And what we're saying is that the length of that vector is going to be in some way related to the length of x itself. So that tells you that x and y are kind of the same space and the bases are the same. Okay, so see why that's a good notion of equivalent. And of course, this is a symmetric relation because if you want to sandwich yi instead, well, you can just take 1 over the big M and M on the other side. And so it's a symmetric relation. Okay, so now let's talk about block bases. So fix basis EI, a sequence yj of the form. So this is really annoying to write. Yj is equal to I equals nj plus 1 up to n, and then j plus 1 in the subscript. It's really small, but I'm telling you it's n, j plus 1 of ai ei, and so these ai depend on, they're different for different j. Okay, this is a yj, it's a vector in x, it's expressed with respect to the ei, but we see that there's these nj's here, which tells you which coordinates you can actually use, and we have n1 less than n2 less than, and so on, is an increasing sequence of, so this is an increasing sequence of numbers, and it is, sorry, I'm halfway through a sentence, a sequence yj of the form that is where, sorry, I'm just going to try to fix the grammar of this sentence, where this is an increasing sequence is called a block basic sequence. Okay, so what does that mean? That means, let me try to draw a picture. So y1 could be, let's just express all of these as sequences with coordinates with respect to the EIs. So y1 might be something, 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 0, something, and then it's 0 forever, right? Because these are, they have finite support. And then y, so that's y1. Y2, we have to have zeros everywhere. Then maybe we can put something here. Okay, and then maybe it's 0, and then y3 has to have zeros everywhere because it comes after these. I hope I line up the zeros. But then now it's free to have some amount of non-zero coordinates and so on. Okay, so that's a block basic sequence. And so you see why they're called blocks, right? Because you can have a block of non-zero coordinates, and then you have to be 0 forever. Okay, so that's a block basic sequence and obviously, oh my God, obviously it depends on the spaces EI, and we could also, am I blocking the, I moved this video to change for you guys. But okay, it's a block basic sequence of EI. And we can also call this a block basis. So block basis sequence, block basis, same thing. Okay, so that's a block basis sequence. Okay, for sets E and E prime of subsets of positive integers, we write E less than E prime if the maximum element of E is less than the minimum element of E prime. Okay, and so how, I guess, sorry, if we let the support of X, that's denoted support, then a block basic sequence just has support of X finite for all J, and sorry, the support of Xj is less than support of Xj plus 1 for all J. Okay, so that's just a way of saying what I drew earlier. Yeah, we're going to use that later. So the definition of a Schauder basis depends on the order of the EI, because we saw that convergent sum. There's something that says if you reorder the EIs, whether it's going to converge even or converge the same value. And so we're going to define some notion of unconditional bases. Okay, so the following are equivalent. So 1, for every permutation, so the following are equivalent for EI, so this is a basis of X. Basis. For every permutation pi of the natural numbers, E pi I is a basis of X. Okay, that's one condition. 2, if AI EI equals 1 to infinity converges for some AI, then it does so under any permutation. All right, so if you have a, it's kind of like the first definition, but now you have a sum and you have all these terms, and if it converges, then it does so even if you permute all the terms. And 3, there exists C such that if AI and BI are such that AI is less than BI, so the norm of AI is less than the norm of BI, for all I, then the sum of AI EI, well, it really ought to be less than, I mean, if the AIs are smaller than the BIs, then this really ought to be smaller than the BIs, but we can't always say that. We can just say up to some constant C. So BI EI. Okay, so that's these are equivalent conditions. Okay, I really wish I could keep them on the screen. I'll just say it. So I'll just say it. I'm just going to write unconditional. All right, because I can't fit the whole sentence. Or C unconditional. So a sequence that, a basis that satisfies one and therefore all 3 of these conditions is called unconditional. And if we want to specify what C it is in that third condition there, then we can call it like C unconditional. So C unconditional basis of X. Okay, so that's unconditional for you. Now let's talk about, there's really a lot of definitions and it's, I'm sorry, but there's a lot of definitions here. Let's talk about symmetric bases. So if you note in C0 or LP, in C0 LP, we have the standard basis EI where it's 0 for a long time, and then at the ith coordinate we have a 1, and then it zeros forever. That's a basis, right? For a C0 for LP, and this basis is interesting because if you each coordinate with respect to this basis is weighted equally in the norm. So if you permuted the bases, and then you rewrite it, and then you take the norm again, you're going to get something equivalent. So what that tells you is that this space is equivalent to any permutation of the basis vector. Okay, and so that such a basis is called symmetric. So a basis symmetric if it is to any of its permutations. Okay. Now, something that turns out to be a weaker notion is actually something called subsymmetry, which is a basis is subsymmetric if it is equivalent to any of its subsequences. Okay, so it turns out a symmetric basis is also subsymmetric, but not necessarily the other way around. And I missed something here. We want an unconditional. So we don't let a basis be subsymmetric unless it's already unconditional. Okay, I believe that a symmetric basis is already unconditional. So that's why you don't say unconditional basis is symmetric. I believe so. Okay, it's in the notes. If you're following the notes, which good on you, then you can see the answer, because I believe I wrote something about that in there. Okay, so we're going to get to our first lemma. Okay, and this the proof's in the notes, but let xi be a bounded from above subsymmetric basis, basic sequence. Then xi is equivalent to the unit vector basis of L1, or xi is weakly null. Okay, so there's kind of a dichotomy between in the space of subsymmetric and sort of the whole family of subsymmetric basic sequences, if they're bounded from above. I think maybe you don't even need the bounded, but I can only prove for the bounded, and that's all we need. So that's the proof I have. So proof notes. Let's write that. I can only prove for the bounded one, and that's all we need. A bounded subsymmetric basis sequence is either L1, and not just L1, it's the unit vector basis of L1, like these guys up here, or else it's weakly null, which means it converges to 0 on the functionals, as far as the functionals are concerned. Okay, and that's as far as the definitions. We're gonna use this fact later, and that's as far as the definitions are going. We're now able to construct Tsirelson space at long last. So I'm going to give a little preamble as to why Tsirelson space was so important. So for a very long time, it seemed like every Banach space had a copy of either C0 or LP in it. Okay, so C0 and LP are these really nice behaved Banach spaces. They're like the classical sequence spaces. They're kind of what you think of when you think of a Banach space, if you're not thinking about a function space, I guess. But even the function spaces have C0 and LP embedded in them. So every infinite dimensional Banach space had a copy of C0 or LP. And people thought maybe every Banach space had a copy of C0 or LP, but it turns out that's not true, because in 1974, Tsirelson constructed this space that does not have any subspace isomorphic to C0 or LP for any finite P. Okay, and the same year that happened, so 1974, another pair of authors, so I'm going to write these down. So it's 1974. There's Tsirelson. I'll print it so you can read it. Tsirelson, and then I don't know how to say it, McGill and Johnson. So Tsirelson actually made the original space, and then McGill and Johnson found a sort of characterization of another space that also doesn't contain C0 LP, and it turns out to be the dual of the original space. And nowadays we call this space T, and we call it Tsirelson space, and that's what we're going to actually construct. And then Tsirelson's original space, even though he calls it T, it's usually denoted T star, just because this one's a lot easier to work with. Okay, so we're going to construct T in this video. Okay, so to construct T, we need to have this definition. So for E subset of n, x in C0, 0, let EX be the, let's just make an example. So if E is equal to, let's say 1, 7, and it's not gonna be in order of 1, 7, 2, 4. Okay, we'll say that. And then X, X is equal to, let's just put random numbers, 4, 6, 7, 2, 0, 5, 1, 3, 6. Okay, well, it goes on forever. EX is it's X, but you only allow the indices that are in E. So we're going to take the first index, that's 4. And then we're going to put this, we're going to take the second index as well, but we're not going to take the third one. We're going to take the fourth one because 4 is in E. We're not going to take the fifth one or the sixth one, and we're going to take the seventh one. So that's 1, and then it's 0 forever. Okay, so that's EX. And I don't want to state the definition, but that's what it is. Okay. Okay, a sequence E1, EK, these are all sets of sets, is admissible if K is less than E1, or it's less than equal to E1, less than E2, and so on up to EK. Note that the K here is the same as the K here. Okay, so it's K sets, and they're all finite. They're all finite sets, and it's admissible if there's K of them. Well, then they all have to be numbers bigger than K, and they have to have disjoint support, disjoint increasing support. Okay, so for X in C0, 0 and any norm on C0, 0, okay, we'd say that this sum I equals 1 to K of EIX, the norms of all of them, is an admissible sum. Okay, so it's just, I mean, if E1 through EK are admissible. Okay, that's just the terminology. Okay, so now we're going to define the norm. So the norm of T, Tsirelson space. Okay, so we start with, for X in C0, 0, we set the first norm, or the 0th norm, to be equal to, to be equal to the L infinity norm. And that's just the soup of the Xi's. So we're going to kind of define a sequence of norms, and we're going to define a sequence of norms on C0. Okay, so that's the first one. On the second one, so for n equals 1, the rest of them are defined as the following max. So it's the maximum of, well, we take the one before, so X of, this is X, norm of X. It's norm of Xn minus 1, all right? Or if this thing's bigger, then it's this. So it's half of the max of I equals 1 to K of EIX. N minus 1, so it's the n minus first norm. So it's half of the maximum of the admissible sums, okay, of the previous norm. Okay, so what are some properties of it? So for all n greater than equal to 0, this is a norm on C0, 0. What else? This norm is less than equal to, so sorry, the nth norm is less than equal to the L1 norm, L1. less than or equal to L1 norm for all n. And it's also increasing. If you notice, xn is always greater than xn minus 1, because if it tried to not be, then you take xn minus 1, or the norm x minus 1, the f minus first norm. So it's non-decreasing, and it's bounded above by L1, so it has a limit. So if we set the norm of x to be the limit of n equals n to infinity, as n goes to infinity, of x sub n, that limit defines a norm. Defines a norm, and t is C00 is the completion. It's the completion of C00 with respect to this norm. Okay, so I proved all these little statements. I proved in the notes, so you can go see that if you're unconvinced, or you just need more time to digest this definition. Okay, so what we've done is we've constructed a sequence of norms, kind of inductively, and we're taking the maximum of them because they increase, and we're taking the limit, so it's kind of the maximum of all of them to be the norm on C00, and then we take the completion, and that gives us a Banach space T. Okay, so here are a couple more facts. So if we let Ti be Ti is 0 all the way up to I, and then 0 after. It's the same as the one before, is what we just call T for Tsirelson space. So the sequence of these guys is an unconditional basis for T. That's a fact. You prove this inductively because it's an unconditional basis. All the n norms are unconditional basis for C00. You take the completions of each of them, and then you just do it inductively. What else? We also have this identity. So x is equal to the max of x of L infinity, or the supremum of a half times an admissible sum. So k of an admissible sum. Okay, and the sup ranges over all admissible sequences. So the sup ranges these are k less than equal to E1 less than EK. Okay. Now you might look at this and be like, what's going on? Because we have a norm on one side, and so it's implicitly defined in terms of itself. And it's interesting because we could actually have taken this as the definition of Tsirelson's norm. That turns out that it's the unique norm that satisfies this identity. And you could take this as a definition because the sets on the other side, well, if one of the sets is not, one of the EIX is the same length as X, then actually what you take a half of it. So there's no, for it to be equal, it would have to be 0, right? And so it means all these EIX are actually smaller sequences. And so you're kind of inductively defining it on sequences with larger and larger support. We start with the singletons, and then we build out the supports of these finite sequences. Then you take the completion. And so that's an identity. And its proof is just kind of annoying. It's in the notes. It's got some epsilons in there. But this identity is kind of it's the only thing we're going to really use if we want to do any kind of serious analysis on Tsirelson space. In particular, it tells us that I equals 1 to k of EIX is less than equal to 2 of x, 2 times x for all admissible sequences, right? Because the supremum of a half of that is less than or equal to x. Okay, so for all admissible sequences, and that we're going to use quite a bit. Okay. Okay, so now we have a proposition. Let Ti be the standard basis of T and M greater than or equal to 1. Okay, for any k blocks yj or j equals 1 to k, where each yj has so I guess 1 over m is less than or equal to yj less than or equal to m. So it's semi-normalized. It's a finite semi-normalized sequence, I guess, of blocks. So each yj is equal to I equals nj plus 1 to n plus 1. It's sub j plus 1 aiti. And for some, and the nj's now have to here, let me write the thing and then we'll talk about it. We need to have this n1 and 2. Okay, so these are blocks with the support of the first block further along than k plus 1, and it's a sequence of length k. Okay, so this might remind you a little bit of the admissible sequence thing, which is kind of where it comes in. If this is true, then we have 1 over n j equals 1 to k ek less than or equal to the norm of j equals 1 to k b. What have I done here? This is j yj less than or equal to, sorry, there's a 2 here, m times the sum j equals 1 to k ej. Sorry, this notation is really horrible. What it's saying is that any any sequence of normalized, did I normalize these? These are not normalized. They're semi-normalized. Any sequence of semi-normalized blocks is equivalent to, if you see on this side, this is the standard basis of L1 to the K, right? It's not L1, it's L1 to the K, the finite version of it. And this is also the norm of L1 to the K. And then we've sandwiched it, right? Which means it's an equivalent basis. So it's saying that any semi-normalized, any sequence of semi-normalized blocks is equivalent to the standard basis of L1 to the K, okay? And that's what this proposition says. And the reason I put it right here is because it actually heavily sort of uses it, not heavily, but it uses this identity. So it's kind of just demonstrating how this identity above here is useful to prove things. Okay, so we kind of know how blocks behave with respect to the Tsirelson norm. All right, so we're almost ready to prove that the Tsirelson space doesn't contain L1. We just need one more lemma. And so we have a lemma. And it's due to R.C. James in a paper from 1964. Okay, if a normed linear space, a normed vector space, I guess, contains a subspace isomorphic to L1, then for all delta greater than 0, there is a normalized block basic sequence. Uj, j equals 0 to infinity. We're going to index with 0 here. You can index with 1 if you want, but we're going to index with 0 here because in the proof later we're going to index with 0, and it's just convenient, such that 1 minus delta, this is delta, 1 minus delta sum j equals 0 to infinity aj is less than or equal to the sum j equals 0 to infinity of ajuj, that's these uj's here, less than or equal to j equals 0 to infinity of aj. Okay, and that's for all aj infinite sequences of scalars. Okay, so the proof is in the notes. And what this is saying is that if you contain a subspace isomorphic to L1, then you not only do so, you can get a block basic sequence that's equivalent to L1 it's equivalent because, you know, it's sandwiched by this 1 minus delta and this 1 here. And you can pick that for any delta. So the delta could, basically, it's very nice. You're not only equivalent, you're equivalent like delta close for any delta. Okay. I'm going to use that to show that T does not contain, because if it did, it would have to do so in this nice way. And T is nothing but nice. I mean, sorry, it's not nice at all. I said the wrong thing. It's not nice at all, so it definitely can't do this. All right, so let's show that now. So this is a theorem we're actually going to prove. It's the first proof of this, I guess, what's becoming quite a long video. T does not contain a subspace isomorphic, so linearly homomorphic, to L1. So proof. Suppose it did. Then by lemma j, with delta equals, we'll pick a 9th, we have a normalized block basic sequence yj, j equals 0 to infinity, such that for all sequences aj, j equals 0 to infinity of scalars, we have 8 over 9, because that's 1 minus delta, j equals 0 to infinity, aj less than or equal to sum aj yj, j equals 0 to infinity, is less than or equal to the sum j equals 0 to infinity aj. Okay, so now in particular, okay, so here's what I'm gonna do. I'm gonna copy this to the next page because I want you to see it while I make another sequence. Copy. Oh, let's put that back and then switch to the next page and paste this. Okay, so of course that's up here. So in particular, taking, so let's say aj is equal to, let's try to draw a brace, 1 if j equals 0, 1 over r if 1 is less than j less than r, and 0 otherwise. So what this looks like is, this is for r greater than or equal to 2, I guess. Does that make sense? I hope that makes sense. Yeah, or 1. It kind of looks like this. You have 1, and then you have 1 over r, 1 over r, 1 over r, and that's r times, and then 0. R times, so then just 0 forever. That is a sequence. We have the sum of j equals 0 to infinity aj is actually 2, because all these 1 over r's, there's r of them and they add up to 1. You add 1, you get 2. So what you actually get gives, so when you apply what we have up there, we have y0 plus 1 over r, j equals 1 to infinity yj, right? That's just saying because y0 is times y1, and all the yj's, it's not to infinity. It's only to r. Okay, so that's just aj yj here. Right, so this is equal to sum j equals 0 to infinity aj yj. And by this, it needs to be greater than 8 over 9 sum of the aj's, which is this times 2, so that's equal to 16 over 9. Okay, and this is for all integers r. Okay, so let E1 up to EK be an arbitrary admissible sequence. Let R0 be the support of Y0. Okay, so if K, so this is an arbitrary admissible sequence, and we're gonna look at the support of Y0. Now, if the support of Y0 is less than K, then E1 through EK, because E1 has to be greater than, the support has to be greater than K, E1 doesn't intersect Y0 at all, okay? So if K is greater than R0, then this sum I equals 1 to K of EI of this vector, which is Y equals 1, or J equals 1, sorry, to R, Y, J. You can throw out the Y0 part because the supports don't actually line up. So this is I equals 1 to K of EI 1 over R, J equals 1 to R, Y, J. Okay, but now we're going to use the fact that for any admissible sequence, the sum of the admissible sum is no more than 2 times the norm of 1 over R sum Y, J equals 1 to R of the vector itself, and this is less than 2. Okay, because well, it's less than the sum of all the L1 norm. The L1 norm is, well, I hope it's 2. Well, sorry, I'm skipping a step here, but YJ is it's a normalized block basis, right? So they all have norm 1, and you add them all up. So it's not the L1 norm, it's the triangle. Okay. Yeah. So we have that less than 2. Okay, but anyway, that's not really going to matter later, because we're going to, in this case, we're actually going to get something bigger, a bigger bound. So if K is less than R0, then we set S to be the set of 1 less than equal to J less than equal to R, such that EI YJ is non-zero for at least 2 values of I. And then T is all the rest of them. So it's 1 less than equal to J R, such that EIYJ is not 0 for at most 1 value of I. Okay. Now, what does that mean? If let's unpack this. So say we have a YJ, okay. Say we have a YJ and it kind of looks like this. This is the support of YJ, and this is the support of the EIs, okay. That's K here, I guess. So these are the support of the EIs. If J is an S, then YJ, let's move it around here. YJ kind of straddles the border between 2 of these EIs, okay? Because, you know, it's, and because YJ is a block basic sequence, let's look at J plus 1. We can't have something like this, right? Because the supports are different. I mean, the supports are disjoint. So if, say, if J is an S, then J picks up one of these borders here. Okay, and there's only K plus 1. There's only K minus 1 borders, because there's K EKs and then there's K minus 1 borders. So there's at most, the size of S is at most K minus 1. Okay, that makes sense. Because each border can only be picked up by 1 YJ. So size of S is less than J minus 1. Okay, T so size of T is equal to R minus size of S. And so the size of T is, I guess it can be as big as Wait, let me figure this out. It's r minus k plus 1. Does that make sense? It's r minus, getting stuck in the middle here. Yeah, it's r minus k plus 1 because the biggest it can be is if s is, t is less than or equal to, the small t becomes small when s is big, and the biggest s can be is k minus 1, right? So it's r minus k minus 1 equals r minus k plus 1. Okay. Okay, so then now we get, so 2s plus t is less than or equal to 2 k minus 1 plus r minus k plus 1, which is r plus k minus 1. Okay. Now, since all the yj are unit vectors, so what this gives us in this case where k is less than or 0 is the sum of I equals 1 to k of ei 1 over r sum j equals 1 to infinity y, infinity r yj. Okay, we can split this up into the j's that are in S and the j's that are out of S. So j in S, and we're kind of rearranging the sum here. So the j's in S, we get I equals 1 to k, of course, of e I yj. Let's take out the 1 over r. I think we'll take out the 1 over. Where's my race? I'll take out the 1 over r here. Yj plus j is in t, the same thing. I equals 1 to k eiyj. Okay, and this is less than or equal to, because each of these we can just bound them by the thing that the identity gives us. So j is in S of, it's just twice of the actual vector, normal vector. But on this side, eiyj, only one of these, so this is a sum of k things, but only one of them is non-zero. So only one of the eiyj's is just one term, and it's at most the size of yj because ei is a subsequence and it's unconditional. So we take the sum of j in t of, well, it's one of the eiyj, but let's not even do that. We'll just put yj. So that's why we got above. That's equal to, or less than or equal to, 2 size of s plus size of t, which is less than or equal to, what do we get up here? R plus k minus 1. Okay. So now we'll go back, and this is just the 1 over, this is just this part. Okay, so we need to divide this by r and add y0. Okay, so what does that give? So sum I equals 1 to k of ei y0 plus 1 over r sum j equals 1 to r yj is less than or equal to, well, let's take the y0 part out. So I equals 1 to k ei y0. I mean, we use a triangle inequality here. And then this other part, 1 over r of the sum I equals 1 to k of ei 1 over r. I keep writing the 1 over r twice. 1 over r should be here. So it's ei I equals 1 to infinity. Not infinity. My notes are kind of bad. J equals 1 to k y j. Okay, I hope I'm not getting it too wrong. If I do, tell me in the comments. I think the notes should be correct, so you should be looking at the notes. This, we'll bound it above by twice y0, which is, because it's a unit vector, it's just 2 times 1. And then here, we took this part before, and we saw that it was r plus k minus 1. So we just put r plus k minus 1 over r. And this is less than equal to 3 because the r over r makes a 1. 3 plus k minus 1. Okay, but k minus 1 is less than r0. I wrote n0. Oh, n0 is r0. Sorry, I think maybe the notes. I don't know if I used n0 or r0. But anyway, so we have that's over r, which is less than or equal to k. 3 plus r0 over r. Okay. So now all we need to do is pick. So we pick some r greater than 2 r0, and so this, the right hand side is at most 7 over 2. So this becomes a half. Is at most a half, and so you get 7 over 2 here. And what does that mean? That means that because this, remember, this is an admissible sum, so times it by 2, and we get y0 plus 1 over r, sum of j equals 1 to k, sorry, r, yj, that's less than or equal to 7 over 4. Okay, but okay, now we're going to get to the contradiction, because we see that this is less than 7 over 4. Okay, but on the other hand, we saw that it is also, this thing is greater than, it's greater than 16 over 9. All right, so what that says is this thing is less than 7 over 4. And it's greater than 16 over 9. Okay, and if you just cross multiply, you get 64 is less than 63, and that's, you know, we got a little bit of nonsense here, and so that's our contradiction. Okay, so that means that, what do we assume? We assume that L1 embeds into T, and we now found that that's impossible. Okay, so there's one more thing to prove. We are going to prove all at once that C0 and all the other LPs don't. So C0, still C0, and we still have LP for 1 less than P, less than infinity. We still need to show that these guys don't embed into T. And to do that, we're going to use something called the Besaga-Pelczynski selection principle. And that says the following. So it's a theorem called S for selection, and it's by Besaga and Pelczynski. So it's Polish names. I think that's an L. Pelczynski, 1958. So let X be a Banach space with basis EI. And let EI star be the sequence of coefficient functionals. And they're given by, so EJ star of X, that's I equals 1 to infinity AI EI. So we take an X, we express it as AI EI, and then we just take the jth term. So it's the functional that extracts the jth term of an expression like that. Okay. So if yi equals 1 to infinity is a sequence of vectors in X such that, so we have two conditions. The first is that the limit, I guess we're not saying that y converges to anything, so I guess we should take the limit of I to infinity of yi is greater than 0. So it doesn't go to 0, it doesn't have a subsequence going to 0. And on the other hand, it is it's 0 as far as the EJs are concerned. So EJ yi equals 0 for all j. So every functional thinks that this yi is 0 because we apply functional to the yi's, you get 0. It's weakly null, but just with respect to the coefficient functionals, which I'm not sure if it makes it weakly null or not. But anyway, it doesn't matter because our sequence is going to be weakly null later. Then there exists a subsequence of yi, which is equivalent to a block basis with respect to the original basis ei. Okay, so it's kind of a lot to say, but we just have these two conditions, and it's going to give us a subsequence that's equivalent to a block basis. Okay, so now we're going to show that. So now we show that. So the theorem T does not contain a semi-normalized subsymmetric basic sequence. Okay, so semi-normalized means there's that m, so it's all between 1 over m and m, and subsymmetric means it's equivalent to all of its subsequences. So as we said before, okay, so T, we want to show that T doesn't contain any of these. Okay, and the argument, it's kind of conceptual. There's not a whole lot going on. We're going to use basically everything we've seen so far. And so suppose, for contradiction, that T contains a semi-normalized subsymmetric basic sequence. Let's call it yi. Okay. So since it's semi-normalized, it's actually bounded above, right? So we showed way back when. Let's see. I'm going to show you to prove it that I showed you this. Might be even further. It's there we go. A bounded subsymmetric basic sequence is equivalent to the unit vector basis of L1, or it's weakly null. Okay, so let's go back to what we were. So yi is either equivalent to unit vector basis of L1 or weakly null. We know it can't be equivalent to the unit vector basis of L1 because we showed before that L1 doesn't embed into T, right? So that's I'm gonna put it in red. It's no way. Okay, so it is it's weakly null. So yi is weakly null, and well, it's weakly null, and because yi is bounded below, remember there's 1 over m less than equal to sorry, you know what I mean. Yi is semi-normalized, so it has that 1 over m and the m on top, and so the norm of any element of yi is bounded below. So the lim inf of the norms of yi's here has to be greater than 0 because it's bounded below, and it's a weakly null. So in particular, these functionals all think that yi converges to 0. Okay, so we now have, we almost have theorem X. Do we have, no, we do have theorem X, theorem S. So there exists a subsequence of yi, which is equivalent to a block basis, which is with respect to the original basis. Okay, so let's write that. So some subsequence of yi is equivalent to a block basis xi of ei, or ti, I guess, the standard basis of t. Okay, so now let's take a subsequence of xi. So xi is a block basis, so it looks like, you know, if we write the coordinates, it looks like that. Let's take a subsequence of it so that the support, so we want, if this is the ith one, so this is the first one, we want 1 to be less than that, and we want 2 to be less than that, and 3 to be less than that. Okay, and it's not really hard to do. You just need to take subsequences. So if, for example, 3 wasn't less than this guy, we'd just strike it out, and 3 should be less than this one. Okay, so we take a subsequence of xi's. So take a subsequence of xi such that the support of xi is greater than the singleton set I for all I. Okay, and then we'll just reindex that so that that's actually xi, and then we reindex xi and yi. So yi had some subsequence that's equivalent to a block basis, and we took a subsequence of that so that the support is all nice, and we reindex yi to that subsequence. Now remember, yi is a subsymmetric basic sequence, so you know, this is now an equivalent. We're taking a subsequence, but it's still equivalent. So it's almost as if we're working with yi itself. Okay, so we reindexed, so we're now working with subsequences. Okay, so since yi is semi-normalized, so is xi. Okay, and why is that? Well, xi and yi span some spaces, and they're linearly homeomorphic, they're isomorphic. And since all the xi's are bounded, when you move them over, you're moving by a bounded functional, so it's bounded above, and then going the other way, you're like going back, you're also moving by a bounded linear functional, so it was bounded below. Okay, so it's xi, i.e., there is m greater than 1, such that 1 over m is less than or equal to xi is less than or equal to m for all I. Okay, now since the support of xi is greater than I, by lemma, okay, what lemma are we going to try to use? We're going to use this lemma. I'm going to be careful where I put it. There we go. So we took the standard basis of t, and now, where's my little pointer here? So for any k blocks of a semi-normalized block basic sequence, all right, as long as you have this going on where k minus 1 is less than the first one, the support of the first one, then we have this, okay? And what that means is that it's it contains a subsequence that is isomorphic to the standard vector basis of L1 to the k. Okay, let's move back here. Sorry, I'm making you all busy. But what that means, so by the lemma, for all n, xi contains a subsequence of length n that is equivalent to the standard basis of L1 to the n. Okay, and so since xi contains a subsequence of length n that's equivalent to the standard basis of L1 to the n, so does yi, right? Because they're equivalent. So you take chains of equivalences. So is yi. Now, so yi has these subsequences that are finite subsequences of length n that are equivalent to the standard vector, standard basis of L1 to the n. Now, if you take each of these, so take each finite sequence, subsequence, and complete it to an infinite sequence. Okay, so now you have all these infinite sequences, and yi is subsymmetric, so it's equivalent to all of them. So for all y, so for all n, the first n elements of yi are equivalent to the canonical basis of L1 again. Okay, that's for all n. So it's interesting because yi has all these subsequences that it's equivalent to all of them, and all these subsequences are sort of equivalent to L1 to the n, and then yi is equivalent to all of them. And so we know the first n elements of yi are equivalent to the canonical basis of L1 to the n, and that means that so yi is equivalent to the standard basis of L1. Okay, and that's a contradiction because what did we assume? We didn't even assume it. We know that yi is not equivalent to the unit vector basis of L1. So that's a contradiction. Okay, so as a corollary, LP 1 less than p less than infinity, and C0 do not embed into T. All right, and why is that? So the proof. Okay, LP and C0 are symmetric, so subsymmetric, and they're actually, so not just LP, sorry, the standard bases of LP and C0 are symmetric. We said that before. You can permute them and you get equivalent. You get an equivalent basis. So it's symmetric, so it's also subsymmetric, and normalized. Right? Each of these vectors has length 1, and so semi-normalized. Okay, that means that if LP embedded into T, you would get a semi-normalized subsymmetric basic sequence in T, and we know that that can happen. Okay, so we proved that T is a Banach space that is that doesn't contain a subspace isomorphic to L1 or any of the other LPs or C0, which is really weird. And this is kind of, I mean, it marked a turning point in theory of Banach spaces almost. In the notes, I'm really not gonna have time to do that, but in the notes, I talk about 3 more spaces. One of them is called Schlimm-Precht space, that is arbitrarily distortable, and that built off of Tsirelson's idea. The norm looks similar. It's a little more complicated, but the same idea of like taking them of inductive sequence of norms, and it's like the max of the previous norm and something else, and some admissible sum stuff, and it's arbitrarily distortable, and you can read the notes to find out what that means. And then after Schlimm-Precht made his space, Tim Gowers and Bernard Mori came up with a space that doesn't have any unconditional basic sequence. So we learned what an unconditional basic sequence was. It was thought that every infinite dimensional Banach space might have an unconditional basic sequence, and turns out that's not true. And Gowers and Mori use a construction that's similar to Schlimm-Precht's, which is in turn similar to Tsirelson's. And then the third space that I talk about is by Gowers, who came up with a Banach space that's not isomorphic to any of its hyperplanes. So hyperplane is a subspace of codimension 1, and yeah, people didn't know whether every infinite dimensional Banach space is isomorphic to its hyperplanes. Turns out that's not true. And his construction is really similar to the Gowers-Mori example. So Gowers is the same Gowers. It's super similar, and it turns out that actually the Gowers-Mori example is also a counterexample to the hyperplane problem, but it was not as easy to prove with that one, so modified it a bit. And all this kind of came back to Tsirelson space. So really, in Banach spaces, you have all these classical Banach spaces, and then you have all these weird ones called the non-classical ones. But all the non-classical ones are kind of inspired by this guy. So this is really sort of a seminal construction in the theory of Banach spaces. Okay, so with that, I'll leave you. I hope that you enjoyed the video. I hope that you maybe took a peek at some of the proofs, because the proofs are really it's analysis. So the ideas are really nice, and it's just covered by a bunch of, sort of bookkeeping that maybe isn't so palatable. But I hope that the ideas shine through if you read these proofs, and that, you get something out of this. Okay, and so with that, I'm gonna stop the recording. How do I do